Thank you. Thank you very much. I hope you are hearing me with this tone of voice. Thank you for inviting me to have the opportunity to give this talk. So I just okay. So I noticed last month you had already a seminar on dark matter, so I'll be slightly faster in this introduction part. But the core idea is, again, dark matter. Why? Because there are various a variety of measurements that tell us that something is off. We don't know that we know that something is not as we expect, and this is deviation from known physics at different scales. I put here galaxy, clusters of galaxy, and even CMB. So what is this dark matter? Technically, we don't know. There are different possibilities. It could be that we don't know how gravity works in these at the scales, or maybe there are astrophysical objects that we haven't seen yet, and that could cause all this gravity that is missing, or there could be another particle or set of particles that we could try to detect. And this the last one is the case I will try to focus on. So in case of particles, the measurements tell us that these particles need to have a certain specific set of properties. Here listed some of those, like neutral, color-free. They must be stable because we still see them, for example. So all of these are reason behind measurements that were performed. Particularly interesting is the weak interaction. It's not the weak of the, let's say, the standard model weak. It's just not very strong, which means that in principle it is acceptable that they can interact with standard model particles. Also, we hope so, because that way we can detect them. And the idea and there are different type of particles that we can try to focus on for the search of dark matter, and the ones that we'll focus on will be the WIMP-like, so weakly massive interactive particles, or something like this, with masses ranging from hundreds of MeV up to the TeV scale. And okay, so how can you plan on finding these particles? Well, you can try to exploit that interaction I was talking about, and this in this sort of ridiculous Feynman diagram means that depending on what you are trying to look for, you can have different strategies. So you can smash standard model particles together and try to detect it by the production of dark matter, as the LHC and accelerators are trying. Or you can detect it by annihilation of dark matter particles that you have in the universe, and try to find some fluxes of particles that you're not expecting from standard model physics. Or you can just try to exploit this interaction, saying, if dark matter comes to me, I have some material that I know, like protons or nuclei, or atoms in general, and they will scatter off, and I'll try to detect what my standard model matter did when it was hit by dark matter. And this is the direct detection, which again is the topic we'll focus on. So for direct detection, we need dark matter particles to cross the Earth, and according to the models we have, that's true. So our galaxy is surrounded by a halo of dark matter particles. They have a certain velocity, so they're moving in all directions, and we are just crossing this halo along with the Earth. So particles are crossing us. So the idea is that when we put like a box of material, and we just wait for these dark matter to hit our nuclei, especially. Why nuclei? Because they have larger mass, like masses comparable to the masses of WIMP that we're looking for. So the kinematic energy transfer is favored with comparison to the electrons, for example. And if you try to estimate this is the formula for the differential rate in momentum transfer and angle, so basically in energy and direction of the recoils. And you see these have is a complicated formula which mainly has 3 different blocks of dependencies. You have which kind of materials you are using, so the kinematics of your target, which is like the parts are in red. Something about the nuclear physics, especially focusing on the which type of cross-section. Usually what you you try to avoid any type of quantum mechanical interaction. We just say they are slow enough that we can consider this collision as elastic. So we just have a sort of generic elastic cross section that could be spin dependent or spin independent. This maybe is something that you heard also in the past. And then you have astronomical parameters. So the local density of dark matter rho zero, and the also the velocity distribution of the particles in the halo where we are. And most of the experiment, what they do is that they integrate the function in all the angles and measure the spectrum of the recoils in the energy. So they measure the energy. But there is one more physical, let's say, degree of freedom, and that is the angle dependence. And I like to do this analogy to show that one more degree of freedom is not always just, they're not all equal and all important. So, wrong. So imagine you have a ball, and if you measure only the wave intensity of the photons scattering off this object, you have a grayscale color. And you can add one more degree of freedom, so the wavelength, and you have a color picture. But adding one different degree of freedom, like the phase, and you get a hologram. So adding just one degree of freedom doesn't give you the same outcome. So it depends what the degree of freedom unlocks you. And in this case, the recoil distribution in the angular, let's say in the distribution of the recoils in the galactic coordinates. So in this angle cos gamma, which is simply the angle between the direction of the sun and the recoil that you had in your lab, follows a peaked dipole distribution. Okay, so and why is this so interesting? Well, the point is that all the type of backgrounds in a, let's say, directional. So if you think of all the background that you can have in your galactic coordinates, what happens is that all the local sources of background that you have at certain positions, so in your angular distribution, thanks to the rotation of the Earth and motion of the Earth around the Sun and so on, in galactic coordinates will end up pretty flat. So at this point, if you just measure energy, you have a somewhat exponential signal over an exponential background. So they can be distinguished, but it's quite hard. Much harder than using a peak dipole structure over a flat background. So this immediately tells you that in case you have no signal already with this, you have a stronger power for making limits. And okay, so directionality means that you can see the recoil angle. Is this the only parameter? Actually, these are the different, let's say, angular parameter in this directionality studies, and they are in order of importance. So the first one is the head tail, which means understanding of your recoil. Where's the head and where's the tail? So where is the recoil going? Imagine an horizontal recoil. You want to know if it's going right or left. And this is the effect that you see here. In case you have full head tail, so your dipole is actually peaked on one direction. And in case you don't have it, so it's actually mirrored in the two hemispheres. Still, it's better than the flat background, but losing head tail, you lose a lot of information, of course. And then the other two are the three-dimensional or two-dimensional recoil structure, meaning you know the 3D vector or just the vector projected on a 2D plane. And then at the end, the angular resolution. So of course, how good you are at discriminating and finding the angle of the particle. The directional advantages are a lot. So in terms of, let's say, limit and potential discovery, since you're trying to find a dipole structure over a flat background, this is better than exponential over exponential in general. But once you get the measurement, so just at the moment you actually get the measurement, you can find the average recoil direction. And this means that you know if it's coming from the Cygnus constellation, which is basically the direction the sun, the solar system is moving towards. And so where the majority of the dark matter particles will come from, just as a inverse motion. And so at that point, you can say, okay, this is exactly as the galactic distribution of recoils that I'm expecting. And it's not something like general excess of energy in a certain region. Is exactly where I want to be. And this means that you can do positive discovery much easier than just energy. Just imagine how many times dark matter seemed like they was found, but instead it was excess or it was nothing. It was just some being in energy. And in this case, you know where the origin is. And in case then, when you have a lot of events, and what you want to do at the end is find, okay, dark matter mass, interaction, but also the other astrophysical parameter is the distribution of the velocity. How is it in the galaxy? And the point is that with the rate distribution, which depends on energy, you have this depending on the distribution of the modulus of the velocity. So you have one dimension. Instead, the angular distribution depends on the vector, so on the three-dimensional structure of the velocity distribution. So you can actually get more information on the astrophysics by doing directionality. And this is just an example, like the latest measurement of the structure of the galaxy suggests that there's a soul surge. It's called the Gaia soul surge. And these are, for example, the differences that you have in galactic coordinates of your recoil distribution with different structure of the 3D velocity distribution. So that's the power of the directional item you get there. Okay, so now we just turn on the detector and look at the recoils. Unfortunately, it's not so easy because we have to remember that these are rare event. So current limits point to less than 1 event per year per kilogram of material. So you're dominated by other type of backgrounds. So of course, the most abundant is the cosmic rays generated in the showers in the atmosphere. So you just go in mines or on the rocks in mountains and you can cover most of it. So let's say that's solved. Then unfortunately you have gamma rays because we're talking about very low energy. So you're trying to get nuclear recoils at very low energy of few keV, and they can be mimicked by electron recoils knocked off by gamma rays coming from the radioactive materials. So you can use, when you go underground, there's the so-called the external radioactivity, which is something that is outside your detector, and you can try to shield this with like high Z material. But unfortunately, your materials is radioactive too. And so there will be gammas. So you have to exploit like detector features so that you know which are the electron recoils you want to project and the nuclear recoils that are signal. Then we also have neutrons, which are even more problematic because they can induce nuclear recoils. So on an event-by-event basis, that's identical to dark matter. But you can try to shield these and try to screen your material and find as more radio pure as possible, and then you have a known background. And unfortunately, at the end, you have neutrinos. Now, in particular about neutrinos, the problem is that at a certain point with large exposure, we'll start having these CEvENs, so these coherent neutrino nucleus scattering. And again, at event-by-event basis, they're exactly nuclear recoils as the ones you're looking for. And there's not really any shield that you can place that can stop neutrinos from interacting and crossing your shield, and it will interact in your detector. And unfortunately, their energy distribution of the energy distribution of the recoils is extremely similar to dark matter ones. So here you have two cases where you have with mass distribution of 100 GeV or 6 GeV, and superimpose the nuclear recoil distribution induced by boronate solar neutrinos and atmospheric neutrinos. And they're extremely similar. So the first statistical study that was performed was saying that at a certain point, you will start seeing neutrinos and you will not be able to see dark matter anymore. And there will be a floor, but you cannot go below that. So it depends on how many neutrinos are actually coming. Or once you see them, you're done. The definition of the floor, and you see the reason why the mass of the 6 GeV is called boronate than other neutrino fluxes, just because of the similarity of the spectrum with respect to what you're expecting as the nuclear recoil distribution induced by dark matter. So this was somewhat still depending on the energy threshold that you have on the target material. So there was a study by Kieran O'Hare some years ago, and he asked himself, is it so unsurmountable? And the answer is sort of, but less than you expected. So the spectra of the induced by neutrino and dark matter are similar, but are not identical. So once you have a lot of events, you can start distinguishing them. The question is, how well is your sensitivity improving with the number of neutrinos that you measure? And so he calculates this number n, which is basically the power of how much your background, your sensitivity is improving with the background. So if you have no background, this n is basically 1 because your sensitivity grows with the exposure, and so the number just goes as 1. If you have a background that you know exactly how it is, and you can immediately eliminate, you usually grow with the square root of the exposure. So your sensitivity will go down as 1 of the square root. So the number n is 2. If you do something worse, your number n grows. And infinity, you have your sensitivity would never grow. And with this, he just plot a new neutrino fog. So you can actually go below the floor, but the fog is denser depending on how closely the two spectra are induced by neutrinos or dark matter. And so you see here that the redder color just means you see number like 10 or 11 of the number n. So here this is the case for xenon target. And you see there's a new definition of the floor. The floor is simply when n becomes 2 for the first time in cross sections. That's your floor, and then down you go with the fog. So this still depends on the target. So changing target, getting helium on argon, you have different fogs. So even if the floor more or less stays as it was before, defined as before, the fog changes. So for example, atmospheric neutrinos are much less a problem for argon, but they are more in the, let's say, 20 GeV masses. So still depending on the target, but you can go there. The point is, when you have these high numbers of n, it's really hard to justify that you grow your exposure by factor 2 and you almost gain nothing in sensitivity. So how do we deal with this? One aspect is try to improve the neutrino flux uncertainties, because if you don't know how many neutrinos are coming, the position of the floor changes, of course. Improving this will mostly, though, not change the fog, but just lower the neutrino floor, so you can then explore that regions with n smaller than 2, but you will not be able to get rid of the fog. Instead, if you employ directionality, you can do better. Why is it? Well, mostly because the majority of the neutrinos are atmospheric, so generated by cosmic rays, so they are isotropic. And in case of solar neutrinos, well, you know where the sun is in any moment. So you know where the recoils from the neutrinos are like on average, of course. So and it happens that what you see here, the ecliptic, so the position of the sun in the galactic coordinates, never overlaps the Cygnus constellation, where you are expecting the majority of the recoils induced by dark matter. Of course, you need good enough directional detectors, so you need a lot of head tail above 75%, and angular resolution that will allow you to actually distinguish when, especially in the time when the sun is closing into the Cygnus constellation. But this way, you can sidestep this problem. And this is just an example. Like if you look at the plot on the right, this is the discovery potential at 9 GeV, so where the boron is. Okay, so this part of the peak here. And what you can see is that the different lines are different type of detectors. So if you just have a counting experiment, it's the one that actually gets the floor. So you just count nuclear recoils and you cannot distinguish them. But you see the difference between having energy measurements, so the orange one, indeed, the discovery potential is improving, but with orders of magnitude of increase of exposure. While instead, directional detectors, especially in the solar case, where you can distinguish them, can lower the discovery limit much better. So, okay, directionality is great. We want it. How you do it? You have to measure the recoil of the size of your nuclear recoils and understand where it is actually going. Unfortunately, these are keV recoils, so especially in like solids. So you can choose your material, solid, liquid, or gases. The one we will focus on are gases, because in that case, gas is less dense, so the track travels longer. The core idea is that the granularity of your readout must be sometimes smaller than the recoil direction. So it was actually made possible also on emulsion layers, so in solids, for tens of keV. So it really depends on how granular you are. But the easier one is the gas. And here I just placed some of the potential directional tests. So you have both R&Ds, both proved to be directional. So Of course, you see the gaseous TPC as a proved technology. There are others with like defects in the crystals, anisotropies on scintillation from crystals, even DNA. So there are a lot of ideas all around there. So focusing on the TPC, you want a granular detector, and a TPC can provide the three-dimensional energy deposit of your recoils. Gas, because we want it longer, and especially if you can play a bit with the pressure and the type of gas to change the density and allow longer or shorter tracks. And since we want rare event, we need large exposures. Of course, this is not great for gases, but you can make them big. And TPCs are generally able to be built with a very large structure. Just a reminder, I don't know how many would know about TPC, but a TPC is basically a particle detector where you have basically a box, in this case full of gas. When an ionizing particle crosses, it ionizes your gas. You have these primary electrons that will be drifted by means of an electric field to your anodic plane. And here you have usually amplification of the signal and readout. And if you have granular anodic plane, you can actually measure X, Y, and Z distribution and characteristics of your recoil. Now, the effort for the gaseous TPC is called Cygnus. We are a protocol operation, so we share information, but there's no. There is a white paper about Cygnus on all of these technologies, and it's basically the idea to have a multi-site, each one developing their own TPC with different technologies, with the idea to reach a multi-site galactic observatory of rare events, both neutrinos and for example, dark matter. And you see both in so there are some in Japan, Australia, Italy, and US. And inside this, you see there's a signal experiment. We are about 50 collaborators in 4 countries. You can see, mostly Brazil, Portugal, UK, and a lot of Italy. And this is part of us at the collaboration meeting. So the idea is to Cygnus wants to build a large TPC, gaseous TPC with directional purposes for rare event searches. The peculiarity of this is the optical readout. So we have our TPC. The amplification stage is made of 3 layers of gas electron multipliers, and then we have an optical readout. Now, which gas do we use? We use helium CF4. Since we have optical readout, we use this CF4, which has great scintillation properties. Here you can see the spectra, the emission spectra of the helium CF4 that we measured. And the mixture is a 60% helium and 40% CF4, which grants you a density about air. So it's quite low thanks to the low density of helium, and a W value of 35 electron volts. So the threshold can potentially be low enough. And also the CF4 is a cold gas, which means that the diffusion inside the gas that you have is quite low, which is important because, of course, you want to measure the direction, so the topology of the tracks, and the less the electrons diffuse, the more information you have on the topology of the event. And for the dark matter search specifically, helium is light. So since we are focusing on low wind masses, the kinematic coupling is excellent for low masses, granting better because with helium, and fluorine as an odd spin. So it can be coupled to the spin-dependent cross sections in the spin. The amplification is made of gas electron multiplier. This is basically a thin layer of insulator cladded into foil of copper. So it's made conductive, and if you put the different voltages on top and bottom of the gel, you have in these holes that are everywhere in this foil. It's a very strong electric field, which allows the primary electrons that are coming to get an avalanche and amplify the signal. And given our gas, here is where the gas breaks and emits photons. So we have 3 stages, and in the last stage we have the largest amount of photons emitted, and those are the ones that we read out optically. Our readout is made by 2 separate detectors. You have photomultipliers too. Why? Because they are fast, so they can provide the measurement of the light. So it's a measurement of the energy. And being fast, you can actually have the temporal evolution of the tracks, and this gives you the structure of the recoil. in the direction along the Z. So all the different elements arrived at the gem at the different times, and you see the evolution. So an inclined track will look like a longer signal, while a track parallel will be looking like a single event. And on the other side, you have scientific CMOS camera, and lately actually quantitative CMOS cameras. Basically, you couple this with lenses, and you can image large areas, keeping granularity of which match the granularity of the gems, so about tens of microns. And they are incredibly sensitive, and they have the quantum efficiency which matches the CF4 emission. So all perfect for that. And in that case, you have again measurement of the energy and measurement of the X and Y distribution of the light of your recoils, as an example here from some tracks. And if you combine the two, you can get a three-dimensional reconstruction of the recoils. Now, just to say why the camera, the great advantage is that when you try to scale up to bigger detectors, you don't have to, for example, when you have 30, 40 square meters of readout, you don't have to fill that with silicon. But you can have like a limited amount of cameras, so with lenses, they can image large areas. The drawback is that the further you put the camera, the larger area you get, the lower photons reach your detector, so you lose intensity. So you have to balance this in order to have good enough gain to see these recoils and a limited amount of sensors. And okay, this was just the evolution of the camera. That's why we are able to use it now, because I mean, just 25 years ago, this was the picture that was made of alphas of NVV tracks. These are tens of keV of electron tracks that we do now. So that's the improvement of the technology that allowed us to do so. Where are we now? We basically just finished the phase 0 of the R&D phase with our last prototype line. We will talk about this. And now we are in the phase 1 of building the 0.4 cubic meter demonstrator of the technology. And okay, so line detector. This was our biggest prototype until we will build the bigger one. And this has 50 centimeter drift with a 33 times 33 centimeter squared log readout, triple thin gem. And you read out, as you can see, with one CMOS sensor and 4 PMPs on the corner. So you have multiple PMT information. And here you see some of the pictures. This is a field case made of rings, some of the images that were taken with the camera when we first landed on over ground. And so it was tested over ground at the LNF laboratories. We just tested the linear response with X-ray sources from few keV up to 35 keV, and then we estimated the background that we would expect, like an average background that we would expect of electron recoil and nuclear recoil if we place this into the underground laboratories of Gran Sasso. Because which was the goal of this detector, was to prove that if we go underground where we have few amount of tracks per second, we can actually operate this kind of detectors, and that our Monte Carlo chain is actually functionally working. So it was installed underground in early 2022, and you can see here a picture of the housing. Lime is inside there. Here you have all the DRQ system with the logic, the HV powering system. Also, we were beta tester of the INFN Cloud project, basically using the common resources to have queues for reconstruction and data monitor. So this was also, let's say, something towards the future of the new small experiments that are not like LHC for the sharing of the CPUs and memory. And then important thing, the gas system not only regulates the pressure inside, but also recirculates the gas. So there's no dispersion of the gas inside the cave, but only 20% of the gas is fresh, and the other 80% is recirculated back inside. Now, how did we operate this detector? So first, it was split basically in 5 runs. So the first run, you only have a field gauge. Then you take data for a couple of months, and you add a shielding of 4 centimeters of copper. a couple of months of data, then you increase up to 10 centimeters of copper, you take some more months of data, then you add 40 centimeters of water to moderate the nutrients more. And this was mainly for the purpose of, can we operate this detector, and for the Monte Carlo chain comparison, because the more, so only with the Faraday cage, the external radiation dominates over the internal radioactivity. The more shielding you place, the less the weight of the external radioactivity, so you can check that your Monte Carlo actually work. And then we remove the water for after 7 months of data of run 5 to actually try to measure the neutron flux of the underground laboratories. This is just an example where you can see line, let's say, naked without shielding, then with a copper shielding over the polyethylene base, and then with the water shielding. And you see also in pictures with the same amount of exposure how at sea level you have a lot of tracks. Then you go there with no shielding, you still have many, but when you put shielding, in the end you have an average of 1-2 tracks per image. So first question that the line had to answer, can we operate with good stability? The answer is yes. The duty cycle is above 90%. Duty cycle meaning how many problems we had, and we had to stop for any reason the data taking. Just, for example, water installation or the winter break. So unless we had operations to do on it, we could take data. And for the last 8 months, which basically corresponds to after we learned everything is these 2 years, we could operate this with a fluctuation of the light yield within 5% for the 7 months consecutively. So this is a good achievement in our opinion, because it says that we can operate it stably for a long time. And then the other one is our Monte Carlo chain working? So here I have to make a caveat. We didn't know how radioactive line was. And so the point was not to prove that we exactly knew how radioactive line was, but that our Monte Carlo chain was correctly representing what we were expecting. So run 1, you see the data in blue and the Monte Carlo simulation and data translation to fake images in red. And that's the energy spectrum. And you see they match. You run 2, you decrease the intensity of the external radioactivity, how much it weights in your simulation, and they start not matching anymore. And in run 3, with more shielding, it's even worse. So that means that there is a contamination we didn't take into account. But as I told you, we just didn't measure what line had inside. The point is that the spectral slope is consistent. So our Monte Carlo chain works. We simply don't know what's inside. And so again, line answered correctly to what was its purpose. Now run 4 and run 5 are under analysis, so I'm not able to show you anything about this. But from line, we also learned other things because we had data, and we are a directional detector. So how good are we at measuring direction? So we have a specific algorithm for this. So this is more or less the chain as it goes. So you have the raw data, for example, the image. Now it's just taken, for example, the 2-dimensional flattening of the image. There's a first code that just finds the pixels are interesting for the tracks. And then you try to find out by the skewness and by the characteristics of the topology of the track where the impact point was, so where the recoil started. And then you weight differently the points, weighting less the points that are far away from the initial start. So every struggling that you have, motion away from the initial recoil direction, you are losing information, and you just care about the first part. This will apply to electrons, and we simulated that data in line that we know now that more or less represents what we see, and we expect some sort of this angular resolution. We use another prototype, a smaller one. We put strontium source which emits beta, so electrons on the side, and we applied the color before. And what we measured was an angular resolution that actually down to 10 keV was below 30 degrees for electron recoils, of course. And the head-tail recognition is close to 100% because we can always get the right direction. So this is extremely promising. We now need to apply to nuclear recoils. How do you get nuclear recoils? We put special data taking with the unvarying beryllium data, so radioactive source which emits neutrons, and so you have nuclear recoils inside. This is the, let's say, a relative of the in the x in the y-axis as a function of the energy. So you can clearly distinguish at high energy, let's say, the different type of population of tracks that you have. So long tracks like MIP-like, electron recoils, and the nuclear recoil band. So if you were to look at the same plot without the unresting beryllium source, the square, the events in that square would not be present. So you know that there you have nuclear recoils. And so these energies, more or less with the quantum factor, is about like 80, 70 keV nuclear recoil. And on those, without applying yet the previous code, what you see is that just with the principal analysis component, you see that when there is no source, the direction is flat. And when you have the source, you have it peaked at 0, where 0 is the position of the source. So you have directionality. This yields something like 45 degrees, but that's without any effort. We want to apply the code I mentioned before, and we are expecting to get again below the 30 degrees. So this was very interesting. And the other thing you can do with this data is to try to discriminate the nuclear recoils from the electron recoils in the region here. So simply, this is not the best plot to see the difference between electron recoils and nuclear recoils at low energy. And the best, let's say, plot or multidimensional plane that we want to exploit, we are trying to find it. And there are a lot of machine learning applications that we're trying. And the preliminary results suggest that above 20 keV electron energy, you basically have 10 to the 6, you can get to almost infinite. So you can read off every recoil. Below reaching down to 4 or 1 keV, we can get, it's achievable probably to get to 10 to the 4 rejection power. Now, another thing, we said 3D reconstruction with the 2 detectors. So we also started working on this, and the easiest thing you can do, LINE provides you, thanks to radon and other decays, alpha decays. So they are long, they are straight, they are exactly like nuclear recoils, but elongated. So we started with them. Camera gives you, this is a raw image, and the intensity actually gives you the direction in the 2D plane, and a measure of the sense of the direction also. Okay, so if it's going again right or left. The 4 PMTs also have an internal structure which give you how bent it is in the orthogonal direction, and obviously the length in the projected direction of we call it Z, is simply the drift direction. Now, since you have 4 PMTs, depending on where the event occurred, you have different distances to the different PMTs. So the light intensity is different. And we employ multivariate Bayesian fit, basically understand from those 4 PMT waveforms where on the XY plane the event occurred. And then we match with the camera. So we can actually say, okay, these events were for the bottom event and the other ones were for the other. So now we can match the 2. And at this point, you can reconstruct a 3-dimensional just by matching where they are going. And with this, you can also calculate you had the length given by the PMTs and by the camera. Now you can have a 3-dimensional distribution of the lenses. Now, if we were to use only the length given by the camera, this would be the distribution of the high energy alpha tracks that we have. When you use the 3-dimensional reconstruction, what you see is that you have much better resolution in terms of length, which in our case is that these are MeV, it's basically energy. Okay, and with this we were able to identify different isotopes for the emitting alphas, including all the random chains, so the random 222, the polonium 218 and 214, but also some others which are components coming from the resistors or on the sides of the
This uranium is actual uranium in the inner chamber, or is it a calibration on the source? So
no, it's an alpha coming from the resistors, because again, we didn't try to make it low radioactivity. This is line data, so we have them. And you can see actually by frequency that where the resistors are, you have many more alphas than you have in the rest of the detector. And so, for example, we understood that we have radon contamination. I mean, we expected it, but once you can actually measure it with this precision, you're actually happy. And this is just the potential of 3D substance behaving. There's also another analysis that confirmed also the behavior of ions moving inside the like polonium ions moving towards the cathode of the detector. So line now is over. We're moving towards NEO04, which means building a much larger detector, 0.4 cubic meter. Now the structure is a double TPC, meaning double phase. So you have two readout planes and a common cathode in the middle. And it will be 50 centimeters each. And the readout plane is a 50 centimeters times 80 centimeters squared. So it's much larger also than what we used in line. Still same type of amplification, three thin gems, and the readout is the same, just higher size. So you have 3 cameras and 8 ellipses per side. The camera is getting a big upgrade, and the new sensor are extremely sensitive to start and be able to get photon counting. And this will be hosted at Hall F at GS. And the purpose of this is prove the scalability. So you prove that you can work with a 50 liter. Now go to 0.4. Can you scale up both the acquisition, data management, and everything like the gauss and all of it? And can you make it body pure? And now know exactly what you put inside, and is the radioactivity and multicolor actually telling you, okay, it's actually what you put inside. So here's another sketch. You see there will be 10 centimeters of copper shield and 1 meter of water shielding outside the copper. The internal side of part of the copper will be radio pure. And inside will be also the PMMA vessel, which contains the field cage. For the field cage, this is a sketch of, we tested with a smaller prototype. Structure made of 1966, which is extremely low radioactive, used also by Borexin, if I remember correctly. And the field cage is, instead of copper rings, we just use a sheet of Kapton of 50 microns with deposited 35 microns of copper, making the strings. And this is a Hall F 6 weeks ago. There you see the back, and there will be all the infrastructure. This is now completed. Now gas system and things are starting to be can be installed now from now. So, about the new sensor, I told you this is much lower noise, and what you can see on the left is the previous camera, and on the right is the new camera with the same, let's say, white to black ratio, and you see how lower the noise in this camera is. It's much darker, so this helps with going low in energy threshold, but the goal is 0.5 keV electron energy. And a few other things that we're working on. So, for example, like what we learn also from line, with the gems will be a sheet of 50 times 80 centimeters squared, like fully with a random segmentation, also to reduce the dead area, but still keep, if a sector gets damaged, not to lose the full gem. And also we are now applying on the gem facing say the optical side, a V-bond technique that just etches a bit more the copper to make it less reflective, because this is a line alpha, for example, and you see there's a reflection. So it was reflecting on the optical window and back to the gems and back to the optical side. And this we proved that removes this issue. So you don't have multiple tracks when you only have one. And for the data acquisition, now we have 6 cameras. We're taking continuous mode. So one image after the other with almost no dead time apart from closing and opening the pixel. But this leads to 10 terabytes per day if you store everything. Of course, you don't want to store everything because most of it is black. Like in this example, you just want to store the pixels that are important for the tracks. And the first things that we tried give us a reduction already of a factor 100, which has actually improved how fast the recognition from machine learning techniques or software is, but this is also promising for data reduction. And in the end, if NEO04 proves that this technology works, then you also have to understand that for physics search, you need a larger detector, like 30 cubic meter at least, or going to the Cygnus size or dimension. And the way we estimated like sensitivity, potential sensitivity of this experiment is based on a Bayesian technique, credible interval estimation based on likelihood fit of the expected background. Inside here, it's still under development to take into account more systematics and more effects, but for sure we include the energy threshold, the background level, the signal distribution and background distribution are in the galactic coordinates, so in angle with some effect of angular resolution that we expect. And the fact that we have a multi-target gas, so we have helium, carbon, and fluorine. And so both of them have different quenching factors elements and different probability of kinematically interacting and being seen. And the expected projection for 30 cubic meter for 3 years of exposure can be seen here. On the left, you have the spin independent. I would say you could look at the bottom plot because now we are mostly sure that we will get to 0.5 keV energy threshold. And so you see that it's competitive a bit with the current status, especially if you consider the other line here, this extension towards lower masses is in case we can also add hydrogen-rich gases. If you lower percentage, they can allow you to go to much lower mass energies. And especially for the spin dependent, it will be very similar to Pico, which is the leading one for, again, carrying fluorine in the mixture. And especially in case we have the hydrogen rich element. So just to say that this technology is not fixed only for dark matter, but you can then use this, let's say, directional detectors for other purposes. In case you have a large detector again, like Genio 30 cubic meter or Cygnus, you can just say, instead of throwing away the electron recoils coming from neutrinos, for example, just consider them signals. And in this case, it is expected that you have some counts from solar neutrinos, and you can start doing solar spectroscopy with large enough detectors, of course. It really depends on the background amount and the exposure, but you can realistically do, for example, PP spectrum at lower energy threshold than Bodex-Hino, for example. And in the other case, with smaller detectors but larger flux, you can do X-ray polarization. It's now a hot topic in astrophysics with the EXP telescope is finding out for astrophysical sources. So you basically get the polarization of the X-rays just by the measuring the direction of the photoelectrons that you have. And we actually did some tests, if you want to know more, and we have some R modulation curves. So I'll conclude just the idea is that we still don't know if dark matter exists or if it is a particle or something different. And in case it's a particle, directional detectors and the assumption of WIMPs is extremely powerful for getting the astronomy and better discrimination powers. And Cygnus experiment wants to prove that optical TPCs are a viable methodology for getting to this directional detection. And we now took 2 years of data offline, which allowed us to improve a lot in this path. And now we're about to build the 0.4 cubic meter detector and we'll see what that detector tells us.